In the last class, we discussed about the first part of application of Gauss's law, where we calculated the field due to an infinitely long straight conductor as well as for a plane sheet of charge, an infinitely large sheet of charge, where one is a linear charge distribution and the second one was a surface charge distribution, and here we are considering a volume charge distribution and it is for a sphere. And a sphere, a solid sphere that consists of charges. A solid sphere, I specifically mention it because there is charges not only on the surface but also inside it. So, there are spheres or there are metallic spheres or there are sphere which has only a spherical shell. In that case, the derivation will be a bit different at the end. So, here I am specifically saying that the charge is distributed not just only on the surface but also inside the sphere there is charges. So, something like in the meat of the conductor itself or in the meat of the material itself there are charges. So, that is the case here we are dealing. So, we have a sphere of radius r. Now, we want to calculate the electric field outside. So, first of all we will calculate the field outside the point, outside this sphere, and we will calculate one for on the surface and then inside the surface, and we can calculate its variation also. Now, what we are doing is we have to first of all we have to construct a Gaussian surface. Let us consider a Gaussian surface. Since the charge distribution itself has a spherical symmetry, we are considering a sphere, a concentric sphere as the Gaussian surface, and we have to calculate the LHS of the Gauss's law, that is the total flux. For calculating that, we have to evaluate E dot ds. So, to find the direction or the what is the angle between E and ds, let me take a very small patch of that, a small portion, and before that our Gaussian surface has a radius small r. That is why I wrote here r is greater than capital R, because we want to find the field at a distant point somewhere over here or on this surface. That means we want to find the field at a distance r from small r from the distance of the from the center of the sphere. That is why we used a Gaussian surface of radius small r. So, for an outside point, the r, the small r will be greater than the radius of the sphere. Now, we constructed that sphere, and next we consider a small patch of that. We consider a small portion of that sphere, and what would be the field at there? Now, we know that it is a spherical surface, so its normal will be directed like this. Okay, the normal will have a direction perpendicular to the surface, and at this point, at some other point, if we consider, it will have a direction like this. It will have a direction, that means it will be radially outward. The direction of the area normal, that is the n cap, itself has a direction radially outward. Now, let us consider the electric field at that point, and electric field due to this distribution will also have the same direction. That means the electric field and the area vector both has the same direction. So, let this be the area ds. So, to find E dot ds, let us calculate E dot ds. E dot ds for this small area, just for this area, if we calculate that, that is equal to E into ds into cos theta. And what is the value of cos theta or theta? That means they are parallel, that is the area vector and the electric field are parallel to each other. That means the angle between them is 0. So, simply this dot product becomes E dot ds or E ds. Now, we got that. So, this is the flux through this very small surface. Now, what we have to find the field due to the entire or the flux through the entire surface, the total closed surface. So, for that, let me write it as this is the case. So, this is what we are up to, and E dot ds is equal to E into ds. Why we put that E outside? Because we know that over the surface of the sphere, over the surface of the Gaussian surface, the electric field is a constant, and we are integrating over that surface. And here at this point and at every point on the surface of this sphere, the electric field has a constant magnitude, not a constant direction. The direction is different, that is here the electric field is towards here, here it is towards here, here it is towards here, but at every point it has an equal magnitude. So, that is why we can take this E outside. So, E into integral ds. Now, what is this integral ds? That is, we only considered a small patch of that is this much part only. Now, we have to consider another part from here, another part from here, another part from here, and these are all small ds parts, and we have to sum it up. The integral means take all the ds part and sum it up. So, when we consider or when we sum it up all, what we get? We get the total surface area of a sphere. Which sphere? Again you see that we are considering the larger sphere. When we are calculating the flux, we are considering the larger sphere, that means the Gaussian surface. So, we have to calculate, or we are in this ds is from the Gaussian surface, not from the solid sphere inside, not from the charged sphere. We are considering the larger sphere. There may be confusions like that. So, be careful when we are calculating the flux of the total flux, we are considering only the outside sphere, that is the Gaussian surface. That is, we need to find the flux through the Gaussian surface. So, for that we take the larger sphere, and for that larger sphere its surface area is 4 pi r square. So, we got it, that is E into 4 pi r square, that is the LHS of our Gauss's law. Now, we want to calculate the RHS. So, for that let me write it as, we know that RHS is 1 by epsilon 0 integral rho d tau. Now, the charge density here is rho. Where is the charge distributed? So, that charge is distributed not on this larger sphere, it is only on this blue sphere where we have the charge. So, let that charge be rho. So, that has a charge density rho and into d tau. So, to calculate this, what we have to do, 1 by epsilon 0 times integral rho d tau. Since rho is a constant, because we have a uniform charge distribution, we can take this rho outside and then we can integrate. So, we can integrate that d tau. So, before integrating that, where we are integrating, that has to be considered. That is, we know the RHS of the Gauss's law, that is, we know that is 1 by epsilon 0 time integral rho d tau. Now, what is this volume integral? So, this volume integral means the volume, or what we are actually doing, this means actually this is 1 by rho d tau means dq. We are summing up the charges actually, but we can change that dq in terms of rho d tau. So, here 1 by epsilon 0 times rho d tau means we are actually adding up all the charges. So, when we are adding up all the charges, we have to only consider about the charge what is inside the sphere. So, inside the sphere, charge is inside the Gaussian surface, the charge is only in this smaller sphere. So, we are integrating over the volume of the smaller sphere, that means the charged sphere, not on the larger sphere. So, the larger sphere is actually r, small r, and there is no charge in between. Okay. Or we can consider it as the charge is only distributed on this smaller sphere. So, we are integrating over it. If the charge is distributed up to this level, we would have been integrated from here to here, some r1 radius. There will be similar cases, we will read it later. So, now that is integral rho d tau means the d tau is, we have to take a small volume from the smaller sphere, and that is our d tau. Now, to integrate that, we have to take another small volume that is also from the same sphere, that is a smaller sphere, and take all of them only from the smaller sphere, because that is the only place where we have charges. So, we are calculating integral d tau, and we know that integral d tau means the whole volume of the smaller sphere, the charged sphere, not of the Gaussian surface. So, the total volume of the charged sphere is integral rho d tau, and we know the volume, that is 4 by 3 pi capital R cube. That capital R is the radius of the smaller sphere. So, we got it as 1 by epsilon 0 times rho into 4 by 3 pi R cube. Now, what is rho? Rho is the charge density. So, let us come to that. And what is that rho? Let us imagine that this charge or this sphere has a total charge of, okay, it has a uniform charge density, but let us imagine that this has a total charge of q inside. So, the total amount of a charge q is distributed over the sphere or on the entire sphere, and that is distributed over a volume of 4 by 3 pi r cube. And now we know that rho means rho is equal to total charge divided by volume for a constant charge distribution. So q divided by 4 by 3 pi r cube is the rho. So instead of this rho here, we can substitute the value q divided by 4 by 3 pi r cube. So here also you see that the volume is 4 by 3 pi r cube. Why? Because we have to consider the charge is distributed only on the smaller sphere. So we have to consider the volume of that smaller sphere, and we get it as, so when we substitute that, instead of this rho we will substitute q divided by 4 by 3 pi r cube. So this 4 by 3 pi r cube and this 4 by 3 pi r cube will cancel, and this q will come here. So the final answer will be q by epsilon 0. So the RHS of the Gauss's law reduces to simply q by epsilon 0, and the LHS of the Gauss's law reduced to E into 4 pi r square. So they belongs to the Gauss's law. We can equate them, that is E into 4 pi r square is equal to q by epsilon 0. So the 4 pi r square will go to the RHS to the denominator. So we got E is equal to 1 by 4 pi epsilon 0 q by r square. And it is a very similar thing, that is it is exactly the equation for a point charge, that is the electric field due to a point charge at a distance r. Here the r is just the distance from the center of the sphere, that is E is equal to 1 by 4 pi epsilon 0 q by r square. Now let us move to the next, and its direction is always radially outward, or we can put it as some r cap. So this will be always, here the electric field will be directed like this, here it is like this, here it is like this, that already we have mentioned. So this is the electric field due to a charge distribution, a solid sphere charge distribution. Now we can calculate it for on the surface of the sphere. So it is very easy actually. On the surface of the sphere, what happens? Okay, earlier we consider a surface which is something like this, and for this its radius was r. Now it is outside, and this has a radius capital R. This was our old Gaussian surface. Now we want to calculate the field on the surface. So we have to reduce this whole circle, or sorry, whole sphere to the surface. So we will reduce that to the surface. So we will consider a Gaussian surface which is exactly same as that of the charge distribution or the smaller sphere itself. Now what is the speciality? The charged sphere has the radius r, and our Gaussian surface also has this radius r. Or simply, when this large Gaussian surface shrinks to the smaller sphere, what happens? The r becomes r, the small r and capital R becomes same. So it is very easy. We remember the old equation, that is 1 by 4 pi epsilon 0 q by r square. Now instead of this r, from this equation r is equal to r, so we can substitute 1 by 4 pi epsilon 0 q by capital R square. This is the equation, or this is the charge on the surface of this is the electric field at the surface. At every point on the surface there will be a radially outward field, and that radially outward field is E is equal to 1 by 4 pi epsilon 0 q by r square. Now let us go to the next part, that is what would be inside the sphere. Okay. Now to find that, let us see. Okay. So this is our old sphere, that is the same charged sphere of charge density rho is equal to q by 4 by 3 pi r cube, and now we have to find the field inside. So we know that this is our capital R, the radius of the charged sphere. Now we want to calculate a field inside it, that means at some point somewhere over here. That means the field point is inside the charged sphere. So we have to construct a Gaussian surface with this as a point. So our circle will be exactly like this. So this is the Gaussian surface. Now the Gaussian surface is inside the larger surface. Okay. Now we have to again do the same things. Let's do that. Now first of all we want to calculate the flux through the larger surface. So that is integral E dot ds is equal to E into integral ds, and the smaller sphere has a radius r. And since it is inside, since the Gaussian surface is inside the charged sphere, it will have a smaller radius than the charged sphere. That is why we wrote here r is less than capital R. Okay. Now we have to find the flux over this smaller surface. So again the field will be normal. So E is equal to integral ds, and E is E into 4 pi r square. The expression for the electric field, the flux, the total flux is same as that of before, but the important is that now this is a smaller sphere which is smaller than our charged sphere. The difference comes in the next part. Now the next part is what we have to calculate. It is the total charge enclosed by this sphere. Now the Gaussian surface is inside. Now what is the enclosed charge? The enclosed charge only contributes, or the enclosed charge is only comes from this area, only from this region, that is inside this Gaussian surface or the dotted sphere. So outside this there are many charge regions, that is this region is actually outside the Gaussian surface. So as per the Gauss's law, we do not need to consider what is outside. So now we have to calculate what is inside. Let's calculate that. For that, 1 by epsilon 0 times rho d tau, which is equal to 1 by epsilon 0, rho is a constant, we taken it outside, integral d tau. Let's wait there. So next part, 1 by epsilon 0 rho, it's okay. Now we have to calculate integral d tau. Now what is this d tau, or from where we have to choose that d taus? So that is, just consider we need the charges inside. So to find the total charge inside, you have to only choose volumes from the smaller sphere. So from here, from here, from here, from here, and from here, not from outside. Why? We need only the count of, or the sum of, the enclosed charge. So we find the sum integral d tau for the smaller sphere, and that smaller sphere has a radius smaller. So that is why here the difference, that is 4 by 3 pi r cube, where we do not need to consider the entire charge. So actual volume of the charge, actually the charge is distributed over the entire volume, that is 4 by 3 pi capital R cube. Okay, capital R cube. What we are only considering what is inside, we do not need what is outside. That is set by the Gauss's law. That is why we are choosing 4 by 3 pi r cube. This is the main difference from the previous one for the outside. Now we can do some modification by substituting the value of rho there. So when we substitute the value of rho, just note that this is rho is equal to q by, okay, q divided by 4 by 3 pi r cube. Here 4 by 3 pi, here 4 by 3 pi and 4 by 3 pi get cancelled, but r cube by r cube will remain. Why? Because this is the radius of the larger sphere and this is the radius of the smaller sphere. So they do not cancel each other. So r cube by r cube will be there, and the final answer will be E is equal to, so we can equate them. Let me do that. That is what we got here. E into 4 pi r square, E into 4 pi r square is the LHS of the Gauss's law, and the RHS becomes 1 by epsilon 0. Instead of rho, we substituted q divided by 4 by 3 pi into r cube. 4 by 3 pi and 4 by 3 pi get cancelled, so divided by r cube by r cube. Now here we have an r square and this cancelled with this r cube, and we can take this 4 pi to here. So what happens? The final answer will be E is equal to 1 by, this 4 pi comes here, 4 pi epsilon 0 q into r divided by r cube. So we got the relation, the final relation as, so let me rub it out. So we got the relation as E is equal to 1 by 4 pi epsilon 0 q r by r cube. That is, here you can see some different relation. We will draw a graph of that, then it will be clear. That is, here as the distance from the center increases, as the usually from the center, as we go from the center, the charge, the electric field will be diminishing or decreasing. Here you can see r is a constant, 1 by 4 pi epsilon 0 is a constant. Why this r is a constant? Because we kept the radius of the sphere, charged sphere, as a constant. Now what is this small r? That small r is the distance from the center of the sphere. So from the center of the sphere it is increasing, that is we can write it as E is proportional to r where it is inside. So inside the sphere the electric field as you move from the center, so as you move from the center electric field will be increasing, which is linearly increasing. Then after coming out, okay, then when we just get out of that circle or the sphere, then what would be the field? The field become the same as E will be proportional to 1 by r square. Okay, then it will be diminishing or a decreasing field. So that is the relation of these three fields. Okay, now we calculated the electric field at outside on the surface and inside the sphere. Okay. So now we calculated the electric field due to this sphere, a solid sphere, for the surface, on the surface, outside the surface and inside the surface. Now let us make a graphical plot of that. So now what we know that inside, I am just drawing only the proportionalities, that is what is inside? Inside the field is E is proportional to r, that is linearly it increases with r, and at the outside E is proportional to 1 by r square. Now based on that we can plot a graph here. Now this axis, that is the horizontal axis, shows the distance from the center. That means here this is the center of the sphere, and as you go away from that, that is we are going out, it is corresponding to this point, this will be the r and this will be the minus r. So inside the sphere means on this axis from this region to this region, that is minus r to plus r is corresponds to the inside of the sphere, and beyond that, beyond minus r and beyond capital R or plus r, they are outside the sphere. So based on that we can draw a graphical representation for that. So let us see. So inside, what is inside? Inside the E is proportional to r, that is it increases with r. Now that means it increases linearly. Linearly means it will be a straight line. At the center it will be 0. So the center it will be 0. Then from there we have to draw a straight line to somewhere to here. And similarly there will be another straight line to here. They will be symmetrical and they will reach a maximum at r is equal to r. That means at minus r and plus r they will reach a maximum. That means the field is increasing. Now after that what happens? After that the field will reduce with respect to or in proportional to 1 by r square. It will fall off rapidly, that is something like this. So something like this. This will be the case, or this will be the variation of electric field for a solid sphere. Again I am emphasizing that this is a solid sphere of charge distribution rho. That means there is charges not only on the surface but also inside. Okay, that means there is inside and outside. There is up to the center we have charges. That is what meant by solid sphere. There are other cases, we will deal it in the next session. So just go to that. Now this is another sphere. The speciality of this sphere, there is not much difference from the previous one. There is a very small difference. All the other results are actually the same. And here you can see that this is a sphere. Here this sphere is not a solid sphere as we seen before. This is a spherical shell. And the charges are distributed only on the surface of the sphere. That is I showed here in the dark blue circle, or this shows the shell. This dark blue region is the shell. That means charge is only distributed there, and inside in this light blue region there is no charge. and imagine this is not a circle, this is actually a sphere. That means only on the shell we have the charge, that is we have a surface the charge is distributed only on the surface of the sphere, and this is another case of a sphere. So, here the results are same, actually you can do by yourself and you get the electric field outside. E outside will be 1 by 4 pi epsilon 0 q by r square, and on the surface which is equal to E on the surface, this is equal to 1 by 4 pi epsilon 0 q by capital R square. Now, what is the difference when we come inside? So, let us calculate the field inside separately. To find the field inside, we have to draw a Gaussian surface inside. Okay. So, I want to find the field at this point. So, for that I am drawing a Gaussian surface. This black line denote or black sphere denotes the Gaussian surface, which has a radius small r and the larger one has a radius capital R, because the larger one is our main sphere, the charged sphere, charged spherical shell. So, now we have to calculate the left side. So, when we calculate the left side, we get E into, that is integral E dot ds is equal to E into 4 pi r square, which is we already calculated for the solid sphere. Now, what is the integral right side or the RHS of the Gauss's law, which is 1 by epsilon 0 times integral rho d tau, or I can write it as 1 by epsilon 0 times integral dq. So, what is the charge enclosed? That is the question. Now, look here, the charge is actually enclosed. What is the charge here? This is the charge enclosed not by the larger sphere, by the Gaussian surface. Now, we drawn the Gaussian surface inside the smaller sphere. Okay. So, we have a larger sphere. On the larger sphere, only on the surface we have charges, there is no charge inside, and we are drawing a Gaussian surface inside that empty shell, that is, it is empty means there is no charges, that is our second. So, our second surface or the Gaussian surface is inside that empty shell, that means inside the Gaussian surface there is no charges, okay, because we drawn it inside an empty region. So, there is no charges inside this region. So, because of that this becomes 0. Okay. Since the RHS becomes 0, LHS E into 4 pi r square is also 0, that means the total E equal to 0. The field inside a spherical shell is 0, the spherical shell and solid sphere, but inside a solid sphere of charge distribution there is charges and there is field, and which varies linearly with the distance from r, but for a spherical shell or the charge distributed only on the surface of the sphere, there will be electric field, there will not be any electric field. All the other regions, that is for the surface and the outside field, they will be exactly same as that of before, and this is the case for that. And let us draw a graph of that too here. So, this is it. Now, we know that this corresponds to minus r and this corresponds to plus r, and inside at the surface there is field, and at the surface here also field, and after that beyond minus r, that means outside it will fall off, and here also it fall off, and inside it is 0. There will not be any field. That means this axis shows the electric field. So, inside there is no electric field. So, the graph will look like something. So, if needed we can draw a line here to show that there is no electric field, and we can connect them something like this. So, this is the electric field due to a spherical shell. This is the difference between spherical shell and this. Now, we have almost done with the what is called basic electrostatics or the electric field. Now, we need something else to calculate the fields more easily. That is, we were dealing only with vectors. We need some scalar quantity to calculate, because we know that the calculation with the scalar quantities are much easier than to do with vectors. So, we need some scalar quantity, and that is potential. So, before going to potential, we need a little bit of digression, that is into the mathematics of vector calculus. I think you better to take another course on that, or you would have learned it in your UG classes, but I will mention just the glimpses or what is important here will be discussed in the next class onwards. So now we are concluding here, and thank you.